Continuing to our next chapter, challenges and solutions in developing optimized and high efficiency auto-trend devices, photodetectors. So as a topic overview, we're going to start off with a recap and the current progress, and we're going to finalize with the future direction. So do you remember what is photodetectors? It is a device that is a optical receivers which converts optical signal light into electrical signal, current or voltage. It is a fundamental element of optical receiver, amplifiers, and signal conditioning circuitry. There are several photodetector types, which includes photodiodes, phototransistors, photon multipliers, and photoresistors, and etc. So what are the requirements that is required for a photodetectors? Of course, we want to have a photodetectors with a compatible physical dimensions, which is small size, which is more favorable. And also, we're going to have a low sensitivity with high responsivity at the desired wavelength, and also a low responsivity as well at wavelength selectivity. Photodetectors should also have a low noise and high gain. Also should has a fast response time, which translates to high bandwidth. Also, we're going to have a photodetectors with a insensitive to temperature and have a long operating life, and of course low costs. For current progress of semiconductor PDs, we're going to look into a PD of indium gallium arsenide, germanium, early silicon, and also mercury cadmium telluride, HgCdTe. Indium gallium arsenide PD. Indium gallium arsenide alloy is currently the most mature material system for photodetection at telecommunication wavelengths. Indium gallium arsenide has a variable bandgap of 3.5 semiconductor with an excellent electronic transport and also optical properties. The bandgap of indium gallium arsenide can be tuned for the wavelength of 0.85 to 3.6 micrometer, making it ideal for near-infrared photodetection. The development of indium gallium arsenide fabrication technology with various PD structures, including p-dope intrinsic and dope PIN. The indium gallium arsenide ternary system is attractive for its wide energy gap, ranging from 0.35 eV for pure indium arsenide to 1.43 eV for pure gallium arsenide. By simply changing the alloy composition, the photodetection responsivity can be maximized at the desired wavelength to enhance the signal-to-noise ratio, especially for the indium gallium arsenide of a composition of 0.53 and 0.47 with the EV of 0.73. So this type of alloy which gives a complete lattice to the indium phosphide substrate and outstanding photodetection performance of a wavelength within 1.0 to 1.7 micrometer. It has a low background doping level and high carrier mobility has also been achieved for the system at room temperature to achieve a good signal to noise ratio SNR under high speed operation. In optical communications, PD based on indium gallium arsenide is currently outperforms silicon and also germanium owing to its direct bandgap properties and also relatively large absorption coefficient, making it capable for covering both of the C and L bands compared to the silicon and germanium that only covered at the C band. So you can see here the wavelength and also the absorption coefficient and also the penetration depth for these different types of materials, which is silicon, germanium, gallium arsenide, indium gallium arsenide phosphide, and also indium gallium arsenide here. So they are exceeding the capability of silicon and also germanium. However, it is difficult to integrate indium gallium arsenide with a CMOS circuit. This is due to the large lattice mismatch between the 3.5 material and also the silicon substrate. and indium phosphide on silicon has 8.1% mismatch. The easiest way to integrate 3.5 with the CMOS technology uses epitaxial growth directly on a silicon oxide insulator substrate, SOI substrate. But this leads to a large strain and high dislocation density, therein reducing the performance and reliability of the PDE. So lateral overgrowth and intermediate buffer layer are also used to improve the crystal quality. But however, the performance is still unsatisfactory. Later on, flip chip integration is used to mate the surface of the detector with the SOI substrate to improve the performance. The major drawback of this technique is that the integration process is carried out on a wafer level, which is time consuming and also expensive. Today, a heterogeneous integration approach is used using wafer bonding process that is commonly adapted to obtain a defect-free 3.5 thin film that can be lithographically integrated with the silicon substrate itself. With modern metal organic chemical vapor deposition CVD technology or molecular beam epitaxy MBE, the indium gallium arsenide absorption layer can be selectively grown on the silicon substrate. Different types of PD structures based on indium gallium arsenide ternary systems has been developed to operate at telecommunications wavelength. The classic PIN structures shown in this figure, which relies on both carrier drift and diffusion to generate the photocurrents. Effenberger and his team propose the use of dual depletion region to improve the device speed of indium gallium arsenide indium phosphide PIN detectors with large dimensions and high dark currents as a trade-off. Later on, evanescent coupling of the PIN detector with a silicon waveguide, a high responsivity of 1.1 ampere watts at 1550 nanometer was achieved and was reported with a low dark currents of 10 picoampere and high QE over 90%. An alternative silicon waveguide butt couple PD with a 9 GHz at 3 dB bandwidth at -4 bias at a high detection speed of 10 gigabit per second has also been demonstrated. Furthermore, coupling of the PIN with a high Q cavity resonator could reduce the dimension of the device while maintaining the value of high QE. 84% of QE was achieved using 200 angstrom of indium gallium arsenide absorption layer. Metal semiconductor metal PD MSM. MSM PDs consist of interdigitated Schottky metal contacts on top of an absorption layer, which are compatible with the current field effect transistors technology. The MSM PDs generally have higher speed and lower dark currents than PIN PDs due to its low capacitance, but suffer from a smaller responsivity. Initially, a thin strain layer of gallium arsenide and aluminum gallium arsenide were used to create a higher Schottky barrier on indium gallium arsenide. This results in high leakage currents and low gains. This is due to the significant amount of trap density exists. Later, thin layers of undoped indium aluminum arsenide were used for the barrier enhancement, which significantly improved the device performance due to the lattice mismatching of indium aluminum arsenide and also indium phosphide substrate. So this is an example of a MSM PDs on a silicon oxide insulator substrate. A researcher introduced a back-illuminated indium gallium arsenide MSM-PD with a record responsivity of 0.96 ampere over watts and a half a 92% of QE at 5-volt bias, but only 4 GHz of bandwidth. However, with coupling with a cavity resonator can increase the bandwidth up to 100 GHz. Recently, a flip chip bonding of indium gallium arsenide MSM diode on the silicon substrate, a responsivity of 0.74 ampere watt at a wavelength of 1550 nanometer was achieved with a 1 microampere dark current under low bias approximately around 1 volt. Chang and his team also demonstrated that indium gallium arsenide MSMPD that is monolithically integrated with a indium phosphide waveguide that fully covers the C and L bands with a nearly flat wavelength dependent responsivity. This is an example of a MSMPD. Indium gallium arsenide avalanche photodiodes (APD). This kind of structure consists of a p-n junction photodiodes. It can operate at high electric fields in order to achieve a photocurrent of more than 1, where one incident photon can generate more than 1 electron-hole pair. In high-speed, long-distance optical communication systems, APD is normally the best choice owing to its internal large gain width, which provides sensitivity of 5 to 10 dB, higher than the PIN photodiode. So this is an example of avalanche photodiode structure on a silicon indium phosphide substrate. Larger bandwidth and higher performance has been reported at 1300 to 1550 nanometer wavelength for various of indium gallium arsenide APD structures, such as separated absorption grading charge multiplication, doped separated absorption grading multiplication. Indium gallium arsenide and indium aluminum arsenide, indium gallium arsenide superlative structures, separated absorption charge multiplication structure with quantum dots, resonant cavity, and floating guard ring structures using a narrow indium gallium arsenide multiplication layer widths, a very low dark current of 10 to 300 nanoampere with a 3 dB of bandwidth and also 80 GHz was achieved. Recent efforts focus on the extending the capability of indium gallium arsenide APDs for the error-free, high-speed modern communication approximately around 50 kbit per second, as well as single photon detection systems. Germanium PDs. Germanium is another photo detection material system at the telecommunications wavelength. Today, fully CMOS integrated germanium PDs are commercially available and share the market with indium gallium arsenide PDs. In terms of material properties, germanium is more suitable for photo detection rather than indium gallium arsenide, although GE is an indirect bandgap semiconductor. It has a small bandgap of 0.8 electron volts, hence granting GE the capability for photo detection at telecommunications wavelength without bandgap engineering. On the other hand, the lattice mismatch between GE and silicon is 4.2%, that is smaller than indium gallium arsenide and silicon, making germanium is a better choice to be integrated with the CMOS circuit. High performance germanium on silicon PDs. In order to develop this kind of devices, this 4.2 lattice mismatch between germanium and also silicon has to be reduced. This lattice mismatch causes the high surface roughness and threading dislocation densities, which degrades the device performance. In 1984, Lurie and his team first obtained high-quality epitaxial germanium and silicon using a graded silicon germanium buffer layer to reduce this threading dislocation density. This method is further improved by adjusting the germanium composition, a growth temperature, and using an additional ex situ chemical mechanical polish step. As a result, a low threading dislocation density of 10 to the power of 6 less is obtained. Alternatively, a two-step epitaxial growth technique has also been developed to directly grow germanium on silicon without using the buffer layer, and a similar dislocation density has been obtained, approximately around 10 to the power 6 to the power 7 centimeters squared. In this addition, this two-step method can introduce tensile strain to the germanium layer during fabrication, which could transform germanium from an indirect to a direct bandgap material, hence greatly improving the optoelectronic properties of the germanium. Other techniques, such as hydrogen annealing, are also adopted to improve the germanium on silicon quality. GEPD also has a similar to indium gallium arsenide PDs, including PIN, MSM, and APD. The early germanium PIN PDs used a silicon germanium buffer layer, suffers from a high dark currents around 0.2 to 0.3 microampere. This is due to the large thermoionic emission even from high quality germanium crystals. Later, Liu and his team discovered that a thin germanium layer of the order of 1 to 2 micrometer could establish a strong built-in electric field, enough to carry us to easily overcome the recombination process at the lattice defects, hence reducing the overall dark currents and significantly improve the device sensitivity over a large bandwidth. An internal QE above 90% in the range of wavelength of 1250 to 1340 nanometer was reported at zero bias. Coupling the device with a resonant cavity could extend the photodetection wavelength to a 1538 nanometer wavelength with a moderate QE of 59%. Coupling the photodiode to a waveguide could improve further the responsivity and bandwidth while maintaining a small dark current. A responsivity larger than 1 ampere watts was achieved with a bandwidth larger than 30 GHz and a low dark current density of 0.2 nanoampere. Recently, with the help of germanium selenide active layers, high-performance germanium PIN PDs are fabricated to extend their photodetection to the longer wavelengths, up to 1800 nanometer. The performance of germanium MSM PD is initially limited by the high dark currents due to the low Schottky barrier height, as a result of Fermi level pinning near the valence band edge. The dark currents can be larger than 150 microampere even after decoupling the photodiode with a waveguide. Efforts were made to modulate the Schottky barrier height in order to suppress the dark currents. For example, O and his team used an amorphous germanium layer to increase the Schottky barrier height and suppress the dark currents by 2 orders of magnitude. Similarly, Laya and his team used an amorphous silicon layer and reduced the dark currents by 3 orders of magnitude. And also, Ang and his team utilized a silicon carbide layer with a reported an extremely low dark current of 11.5 nanoampere with a high responsivity of 0.76 ampere watts and a QE quite moderate, it's around 60%. An alternative method of reducing the dark currents is through the adoption of dopant segregation technique. For example, implanting and segregating the arsenide and boron or sulfur dopants can suppress the total dark currents by 3 to 4 orders of magnitude. With this modern fabrication technology, the responsivity of germanium MSMPDs has been boosted to 1.7 ampere watt at 5 volt bias. Germanium on silicon APDs combines the germanium properties with a excellent optical absorption and also the outstanding carrier multiplication properties of silicon, since silicon has a smallest ionization ratio K value, approximately around 0.1, than 3,5 materials such as indium phosphide with K value of 0.5. The germanium on silicon APD is believed to be better than 3,5 APDs in the high-speed optical communication systems in terms of higher gain bandwidth and also a better sensitivity. With a simple germanium silicon on silicon strain structure, the multiplication factor can be larger than 50. Kang and his team achieved a gain bandwidth product of a 340 GHz with a small K value of 0.09 and a sensitivity of 28 dBm at 10 gigabit per second. Masafane's team manipulated the optical and electrical field within the germanium layer and achieved 70% of noise reduction with a high photodetection speed over 30 GHz at a 1.5 volt bias. With the state-of-art fabrication technology, as you can see here in this picture, the multiplication gain has been boosted up to 680 at 8 volts of bias. The speed increased up to 43 gigabit per second at 1550 nanometer wavelength with a bit error of 10 to the power 12. Meanwhile, the input power output can be reduced as low as 35 dBm. Thank you everyone. Take care and have a good day.